Thank you very much. So first I want to thank the organizers and a wonderful conference. I'm extremely happy to be here. As I mentioned to people, I was here once before in 1987 when there was a conference on heavy fermions here. That's quite a famous conference. I was a postdoc, and it left a lasting impression on my scientific career and also on my love for India. So ever since then, I've been back. 87, 88. It was in
RVB.
The RVB conference, yeah. That you missed. But it was, anyways, the first time, and then I went back 6 more times. So I want to talk about something that is not completely mainstream. It's to look into transport theory, really basic transport theory, because people who do correlated electrons and now strong spin orbit physics find that the most difficult thing is to try to describe transport in a metal rather than in a system which has a gap or which has a very simple transport properties due to incompressibility and such things. But in metals, we have gapless excitations and scattering, and one has to solve very complicated, sometimes very complicated Boltzmann equations. And then it turns out the Boltzmann equation is really invalid in many of the most interesting cases. So this is actually a talk about new developments in transport theory that I believe would be helpful in quite a wide range of systems. We only started applying these formulas just to see how they work, but there's a lot to explore still. Anyways, there's papers here that you can, well, the ones that are out, you can look at details, mathematical details, which are a bit heavy, but not insurmountable. So let me see. In cuprates, there are Hall anomalies. What does that mean? If you look at one of the most earliest Hall resistivity measurements in LASCO, as a function of doping away from the Mott insulator at this point. So here you're doping with holes, so actually electron filling is this way. There is a divergence at what would be counted as half filling. That is definitely not a Fermi liquid effect, because Fermi liquids have diverging Hall resistivity only in the bottom of the band and the top of the band. And that was pointed out that this system somehow funnily behaves as a semiconductor when band theory and Fermi liquid theory tells you, no, it's a large Fermi surface system. Why should the Hall coefficient diverge? Second interesting anomaly is in the superconducting phase, not just of cuprates, but many systems which are superconducting. Below the critical field, there is transport. It's called flux flow. But most interestingly, the Hall sign reverses, and that's something that's been controversial and discussed over many years, and I'll discuss some recent development that we did on that. And this is the most convincing transparency that shows that in the cuprates, as a function of doping, there's a lot of very strange behavior. And now why do I concentrate on the Hall resistivity? Because that is used by experimentalists to characterize very simple quantity, which is the number of carriers. And that is one of the questions one can ask. Is it really the number of carriers? And I will show that it is not, but it's not far away from that. And that's the punchline of this talk. So the Jude analysis is confusing. So what does Jude theory say? Jude theory says if you have a magnetic field and a cyclotron frequency given by that, sigma xx in the limit of omega c tau less than 1, which is the limit of most metals at reasonable fields, you get the usual Jude formula. There is a scattering time there, effective mass, and a density. And if you look at sigma xy, well, sigma xy is even more complicated. It has the scattering times squared. It has the effective mass, and it's given by this Jude formula. If you take omega c tau much larger than 1, very strong magnetic fields such that you open up a large gap between Landau levels, then sigma xx goes to zero temperature, and sigma xy becomes very simple. It gives you the Galilean invariant result. However, much of the current discussion is always about gapped system, topological insulators and such. And when you have a gapped system, life becomes simple. Sigma xy is given by a thermodynamic quantity, it's called the Streda formula, or a Chern number. Both of them apply when you have a gap. And they essentially give you a quantized, in the case of quantum Hall phases, they give you quantized values of the Hall conductivity, but notice sigma xx has to be 0 in order for these formulas to hold. So what happens if sigma xx is non-zero? One should go to a theory of metals. The Drude Hall coefficient is actually simple. You take and invert the tensor, and you use the reasonable assumptions of a metal that sigma xx has some limiting value at 0 field, and then at magnetoresistance goes like b squared. Sigma xy by symmetry goes as an odd function of b, and when you take and inverse the tensor I showed before, you get that d rho xy, d rho yx, db at 0 field is a quantity called Hall coefficient. And if you plug in all those expressions from the past transparency, the effective mass cancels out, the lifetime cancels out, and it just depends on one over density times some universal constants. So this is an equilibrium quantity, and we're talking about transport. So how can we use an equilibrium thermodynamic average to describe something that depends on currents and scattering and so on? That's like a miracle that happens in Drude theory, which gives you a result that's independent of the effective mass and the scattering time. And the question that is posed, was posed for many, many years. Is this general? Is this beyond Drude theory? Or is it just a weak coupling artifact? So beyond the Drude theory, of course, there's band theory. Band theory has strong potentials, but they're lumped into the effective band structure. And Boltzmann theory applied to band theory gives us, again, the same miracle. It gives us that when you calculate the Hall coefficient, it just measures some static equilibrium quantity which is related to the Fermi surface shape. For instance, if you take a tight binding model in 2 dimensions, this is the nearest neighbor hopping model. If you have low filling, it's electron-like. If you have high filling, it's hole-like. The Hall coefficient simply crosses 0. Here it diverges like 1 over density of electrons. Here it diverges like 1 over density of holes. Here it crosses 0. No divergence, by the way, at half filling, and contrary to what we saw in cuprates. And if you want to say, oh, I want to get below half filling a positive sign like the cuprates show, let me add next nearest neighbor hopping, you'll get a slightly different band structure and a slightly different crossing. But again, this quantity will be finite. Okay, and that's what band theory can give you, or Fermi liquid Boltzmann theory. Now, there are materials that we know Boltzmann theory shouldn't work. These are called bad, and recently they've been nicknamed strange, failed. I think all these names are by Steve Kivelson, my advisor, so I should take these names seriously. Anyways, the DC resistivity exceeds a Yoffie-Regel bound. That's actually very old bound that people have noticed and worked on. When it exceeds the bound and you translate it in Drude theory to effective mean free path and scattering rate, you get that the mean free path is very short. So short that it's shorter than the distance between particles, so therefore you cannot really describe the system in terms of independent quasi-particles. And that's why people have to look for different ways of calculating transport, because Boltzmann equation is really invalidated just by the data, not by theorists. However, calculating the Kubo formula is not easy, as anybody who does numerics know. If you want to calculate a DC conductivity, you have to take the order of limits in this order. First, you have to take the thermodynamic limit, which throws away a lot of the possibilities of doing exact diagonalization on finite systems. And then you have to take the limit of the other parameters to 0. In the end, you take the dynamics to 0. So it's intrinsically, even the DC limit is a dynamic dissipative quantity in a metal. And there's lots of problems with many methods. One perturbation theory I don't want to go into because it's not applicable here. What? Epsilon is this epsilon prescription that you add in the delta function. So perturbation theory is difficult. I mean, it's doable for weak disorder, but it involves resummation of many diagrams because you're starting the perturbation theory around an infinite value of the conductivity at zero disorder. So this is one of the problems. And then if you want to add strong interactions, life becomes unbearable. Real-time response by numerics is ill-posed because you have an exponent that you have to expand at long times. And this is a very bad operator to treat numerically, called killed by discretization at long times. And DC is, of course, long times. Analytic continuation of imaginary time quantum Monte Carlo, when there's no minus sign problems, still is problematic because you're always limited to frequencies larger than temperature. And the linear continuation itself is ill-posed in the DC limit. High temperature frequency expansion, again, you have to expand in terms of this operator, and that's difficult. There is a method that we worked on, it's called continued fractions. It does give results, and in cases where you can check numerically that it converges, it's okay. However, it requires extrapolation. It requires some ansatzes on the shape of the conductivity, dynamical conductivity function. So then I asked the question, what about the Hall coefficient, the Hall resistivity? Well, the Hall resistivity is a ratio of two conductivities, so the first thing you say is twice as difficult because you have to calculate both sigma xy and sigma xx. And the question, is it doubly challenging, therefore? And the answer, surprisingly, is no. And that's what the formulas I'll show you will give. So contrary to DC transport, which I said was difficult, there are quantities that people have been calculating on even complicated many-body models, which are equilibrium coefficients, static susceptibilities, spin susceptibilities, compressibilities, stiffness constants for superfluids, and so on. These are doable because they are essentially derivatives of equilibrium free energy. And by that, there's many methods that have developed over the years in statistical mechanics. Low temperature, you could use variational wave function. You know a lot about DMRG in tensor networks. That'll give you a nice estimate of energies and their derivatives at low temperature. Quantum Monte Carlo, if there's no minus sign problems, does not need analytic continuation to get thermodynamic quantities. You can evaluate in imaginary time and keep the results. High temperature is even easier. So unlike scattering theory, it becomes difficult at high temperatures because scattering goes up. Do high temperature series expansion on susceptibilities, it's very easy because you start with a trace at high temperature and then you have powers of traces, and you can, in principle, a well-developed method to get susceptibilities in a beta expansion. And you can also replace the quantum Hamiltonian with the classical Hamiltonian at high temperatures and use classical Monte Carlo with no minus sign problems. So there's many methods, and this is just a tip of the iceberg. And what I'm emphasizing is that this is what I call computable. When I say computable, it means there are methods, they converge, they have been checked on many, many systems. Okay, so now as a slight interlude, I'm doing it very short because I want to get to some punchlines in the end. The details are in the paper, but I want to just point out that there's some very interesting mathematics that I had to run through in order to do the derivation of that formula. And that was using the hyperspace representation of the Kubo formula. So Kubo formula, you think of it as some matrix elements and delta functions and so on. But there is a way to write it as a matrix element, a diagonal matrix element of an inverse of the Liouvillean in operator space. So the Liouvillean is a hyperoperator. It acts on operators, the commutator of anything on the right with a Hamiltonian. The inverse of that has to be applied to the current and then take a matrix element with the current. This matrix element is nothing but these cross susceptibilities we discussed before that are computable. So this is just a formal expression, and the question is, what is the use of a formal expression? Well, it turns out that it has use for both for sigma xx and for sigma xy. What I'm going to use it for is for an expansion in magnetic field. So what I'm interested in is taking derivatives with respect to magnetic field. And this is a very convenient starting point because all these guys depend on magnetic field. You can take the derivatives by chain rule, and apparently many of the terms will vanish, and we get some very interesting formula from that. That's essentially the whole reason for using this hyperspace notation. Now, for the longitudinal, I'm just mentioning, because it's not the topic of, so this is the formula I'm getting. I'm finding the derivative of the whole with respect to magnetic field at zero field is given by this matrix element, which depends on the inverse Liouvillean and the hypermagnetization. It's the magnetization operator commuted with anything on the right. This guy here turns out, in a miraculous way, to be proportional to sigma xx, the conductivity squared, times something. And what that something must be RH, because RH is this divided by sigma xx squared. So there's an expression for RH that does not involve all the dynamics and the dissipative order of limits that go into sigma xx, because it cancels out. And that's really the source of the reason that we eventually end up with a formula for RH that is non-dissipative and is essentially a thermodynamic quantity. So it's like a generalization of the fact that tau squared canceled between sigma xy and sigma xx squared in inverting the conductivity tensor. Now, if anybody's interested in doing dynamics using continued fraction, this is the starting point, and these are papers doing that. Best is to read this book that has a lot of tricks of the trade. But I'm not going to discuss that here. So what is the formula for RH? The formula for RH, this guy, is separated into two parts. One is an important part. One is a term that needs to be calculated, but in many cases it's small, and we'll show when. So the first term is nothing but essentially, you want here an expectation value of a commutator between the polarization in the x direction, the magnetization, and the current in the y direction, divided by the sum rule, which is the normalization of the current. So that's essentially the formula that I'm going to use for the TJ model and other models. There are corrections. It's an infinite sum, but all the terms in the sum are also given in terms of these equilibrium coefficients. You say an infinite sum is a problem. Well, it could be if the terms are large, but those could be computed one by one, and in many cases, they just decay fast as a function of order. So they'll give you corrections. They depend on multiple commutations of the Hamiltonian with the currents and the magnetization. And in principle, doable. That's essentially the formula. The formula itself, as you can see, is something that already gives us a lot of insight on what really goes on when you are talking about the whole coefficient. So that's the bottom line here. And there are two other formulas which we haven't yet exploited, but I heard very nice talks about thermal transport, thermomagnetic transport today. So this is formula to calculate the Nernst coefficient. So it's not alpha xy, it's alpha xy divided by sigma xx, kappa xx. It's a modified Nernst coefficient. The Nernst coefficient has some whole resistivity in it also, and alpha xx. But this term here is also thermodynamic and could be written in terms of this ratio of matrix elements of operators, except you replace one of the currents with a heat current. If you replace both currents with heat current, you get for free an expression for the thermal Hall coefficient. So recently, the thermal Hall coefficient became very interesting in quantum magnets, in both experimental and theoretical work that was done on spin liquids and now on the cuprates. So this formula here will allow you to get the thermal Hall coefficient, which is when you apply heat from one side to the other, you will measure a temperature gradient on the transverse direction. So you'll shove in a heat current, which is what is done experimentally, actually. It's, by the way, Hall resistivity is what most experimentally measure. They don't measure the conductivity because it's easier in a bar geometry. Anyway, so this is the three formulas, and now we'll see what, first of all, do we recover known results? Well, of course you should. It's an exact formula, but it's also easy to show that if you have weak disorder in your band structure, then the zeroth order term is the only one that's left. And the zeroth order term is written in a very simple way. Has the magnetization commuting with one of the currents, multiplying by the other currents. If you write it in band theory, you'll get this expression where f of k comes from this commutator. And this is an expression that takes, I don't know, a few pages in textbooks to derive from Boltzmann equation, because there you have to calculate sigma xx, sigma xy, invert the matrix, so on. So it's actually a very fast way of getting the Boltzmann result. And this is the curvature of the Fermi surface in the constant lifetime approximation. That's Boltzmann theory. I just want to mention that I found out that even within Boltzmann theory, if your band structure is complicated, has several bands, has spin-orbit coupling, I don't know of any closed formulas for strong spin-orbit but this allows you to do that. So now, if you have strong disorder, like an Anderson localization and so on, the higher order corrections must be calculated, and they're important. Also, if you have strong many-body interactions. But that's, again, something which is doable, even in a case where you don't have quasi-particles. So, cuprates. So, cuprates, as you know, have a very interesting phase diagram. At half filling, it's a Mott insulator, and then it has pseudo-symmetry between holes and electrons. Therefore, Anderson proposed very early on, in fact, here in Bangalore, he proposed that the best way to understand the superconductivity is through the Hubbard model. And why? Because the Hubbard model at half filling is an insulator. Now, at the time, everybody thought the insulator was a charge disproportionation insulator. But Anderson said no. He talked to the local chemist here at the IIC, and they convinced him that it's strongly interacting and it can't be charge density wave. It has to be an antiferromagnet. And I don't mention the names of people who argued with him, but within 2 months, the antiferromagnetism was found, and people start working on this model. Now, this model, if you go to lower temperatures, could be described by the TJ model, which is a projected model. That's actually a model that's easy to do computations on. It has less degrees of freedom than the Hubbard model. It has this kind of a symmetry between particles and holes. The reason I write stuff here is because a lot of the arguments in the field have been about what to add to the Hubbard model to make it realistic. The problem was nobody ever calculated any transport coefficient of the Hubbard model without the stuff, so why argue about this stuff? Anyway, so here is the Hubbard model. Here it's reduced to, to the Kurzweiler projected fermions, and you get the TJ model. The first term you get is the hopping term. It's with a gauge field here. These are projected fermions, are not simple. They have complicated commutation relations, but low density, they do describe electrons hopping in a band structure, but at high density, the projection becomes important, as you'll see. And then there's 2 other terms. So there's a Heisenberg exchange that gives rise to antiferromagnetism at half filling, and then there's a second nearest neighbor hopping that is important actually for the whole effect. I'll show you soon. Usually people throw it away. This book, you can see the derivation and how this term comes about. The higher order terms are of order t cube over u squared. So this is the result. It's an analytic result for the high temperature TJ model, hole resistivity, 0th order term. It has 2 contributions. One of them is very simple. It diverges towards the Mott insulator with the positive sign. Notice that in band theory, you should always get a negative sign below half filling. This is without nearest neighbor hopping. So just taking the pure nearest neighbor model, the sign reversal here is totally from interactions, not from changing the band structure. But the most important is the divergence. Divergence is not exactly 1 over x, but it's some factor times 1 over x. And it's given in this high temperature limit of the TJ model. The second term comes to this next nearest neighbor hopping. The reason it has a power of temperature is because it closes, in the new high temperature series expansion, when you close a triangle, you get 1 factor of beta less. So you get 1 factor of temperature higher. So this term you see is not very important because your temperature is much below T, you can neglect it. But if you take the temperature to be of order U, and this becomes important. And what does it do? It pushes down this divergence. So this shows you the crossover to the Hubbard model. Because in the Hubbard model, at infinite temperature, the interactions are not important. Okay? Double occupation, single occupation, all the same infinite temperature. So you get this kind of a band theory back at really infinite temperature of the Hubbard model. But the TJ model, you get this divergence. And that's, of course, well into high temperatures because we're talking even T is of order 2 electron volts and higher. So this is not something that's related to any experiments in cuprates, but is related to simulations of these things on cold atoms. So we look at it. So this is work in which is in preparation with also the Stanford group. So this is the experiment that we're referring to. By the way, to get the idea, why do you get this high sign reversal next to a Mott phase? Well, there is this effect that when you crowd the bosons or crowd the particles next to a Mott phase, you have a reversal of the Hall sign because what is really moving are the holes. So it's not a particle-Hall transformation you're used to from fermions. It's just a kinematic constraint that is building up when you come close to a Mott phase, even for bosons. So for bosons, it's been shown before by Netanel Linder and Sabi Huber and myself that there is a sign change between the Mott chain, exactly at halfway between the Mott phases, something that maybe should be checked, called atoms. But what is nice is now it also carries on to this formula for the Hall resistivity. And to calculate the formula, you need to write the right models. So the models for between the Mott phases, model of XY model, hardcore bosons, and the models for the Mott lobes, the end of the Mott lobes is Gauss-Pitayevsky, relativistic Gauss-Pitayevsky or relativistic O2 model. And they give you these sign changes according to this map. So that's a similarity between the TJ model, which is also the reason for the positive Hall effect and the diverging Hall effect is the fact that you're crowding the electrons and the only thing that can move are holes. And that's the effect. So it teaches us something about Hall coefficient. Now I'm, what's my time? Ooh, okay. So this is actually a completely different, but not completely different issue. This is the issue of Hall anomalies in superconductors. So in the superconductors, this phase diagram of HT, where you have an HC2, but you also have flux melting. Between the two, there's flux flow, which is vortices can move. You have to push them a little bit, but then they move and they give you a voltage. So it's not really a superconductor per se, but it's very close to one. And Bardeen and Stephen wrote a very nice theory back in '65 saying that the resistivity here is very simple. It's going to be linear in B over BC2 for the resistivity and quadratic, because this goes like B also, for the Hall coefficient. What's most important is the Hall angle. The Hall angle is going to be the ratio of the two, and it's exactly the same as the Hall angle that you'd get in the normal phase. So the Hall angle doesn't care about superconductivity. So it stays the same sign, for instance. It won't change sign. This was their prediction, and immediately after, or quite shortly after, people started arguing with them, said, no, experiments show changes of sign in this regime. And that was called the Hall anomaly. What happened to the carriers? Suddenly they decided they're not electrons anymore and they're holes because you cooled below TC or below BC2. That was an open question. I still is because people argue about it, but I think we now understand what's going on here, and that's actually revising the theory of flux flow. So this is very closely to these are very old experiments from '75 showing Hall sign reversal in vanadium and niobium. This is very recent. In BISCO, they showed these Hall sign changes. And the theory that is written just came out 2 days ago in the archive, successfully accepted to the archive, as my friends say. The picture is the following. Contrary to much of the vortex dynamics theories that you might have heard, it is not a good idea to get the Hall coefficient correctly to try to theoretically shove a current and look for a voltage. That's always a bad idea in many body systems, because Hamiltonians like to have parameters putting into them, like fields, and not currents. But that's a side remark. The point is that if we take this problem and impose a voltage, impose an electric field, only two things can happen. Either the superconductor will burn up and explode, or vortices will start moving. And not only will they start moving, they will start moving exactly at the velocity given by this equation, which has no parameters in it. No lifetimes, no mass, no nothing. This is called Josephson relation, but I'm using it to derive what is the average velocity of the vortices and not what is the voltage the vortices create. It sounds like the same question, but it's different. Because now we know the vortices are moving in a particular direction, completely perpendicular to the applied voltage at a particular velocity, and the question left is what is the current doing? So you have to look for the generators of current in this system. Okay, so doing that, you get two contributions to the current. One is core currents. The cores act as pumps, and that will give you the Bardeen-Stevens result. But there's another term. Each one of these vortices is charged in general. It's carrying some charge with it. Could be zero, could be plus or minus, but if it moves, that charge will give you a Hall current, and that's the magnitude of the Hall current. So how much charge is accumulated, you can calculate from the Ginzburg-Landau theory, and it depends on the parameter, which is how much the superfluid density changes when you change the electron density, or how much is the doping-dependent superfluid stiffness. Now, in vortex physics, we know that if we change a little bit the magnetic field, we'll change the charge with it, because everything is rigidly attached to the vorticity density. If there is some kind of a current charge in the unit cell, that charge will be associated with one vortex, and if you change the number of vortices, you'll change the charge. So that local attachment is called local flux charge attachment, very familiar from quantum Hall. But here it's actually very physical, because it means that this correlation function between magnetic field and charge is local in space and time. When you Fourier transform, you get a function who is analytic in Q and omega, and you can change the order of limits. One order of limits is the DC conductivity. The opposite order of limits, this is the thermodynamic order of limits, is called the Streda formula. And that formula is only applicable if you can change the order of limits between Q and omega. But here you can, as you can in the gapped quantum Hall. And therefore, you have an exact prescription for the QV. The charge of the vortex is the change in the charge as a function of adding one flux into the system. And then the screening, which I don't have time to talk about, but it requires to have screening off the axis, off the plane, in a dopant layers, or if it's a two-dimensional superconductor, it has to be in a backgate. But once you have that, you get a contribution to the Hall charge that can flip the sign. These are experiments done at the Technion. They very nicely analyze the Hall resistivity, and this is the longitudinal resistivity. And they took the Hall angle from the normal state, extrapolated it down to the temperatures which are interesting, and subtracted the Hall conductivity from the Bardeen-Stevens conductivity, which is Tangens Hall times sigma xx, which is measured, and evaluated QV, and it went like, it fit very well, as you can see, the logarithm of the magnetic field, which is the theoretical prediction from the Ginzburg-Landau. And therefore, and the magnitude, by the way, is about 1 electron per vortex. So, and this is analyzing experiments done by Philip Kim's group at Harvard. And what's nice is I took 3 cuprates from different, this is one of them, there's 2 others, 1 electron doped, 2 Hall doped. They have very different TCs, very different superfluid stiffnesses, but when you extract the charge, you get numbers which are not very far away from each other, and you also get the electric constant, which is quite similar, which you expect, because these are all cuprates. So that's very satisfying. It has the right signs also, as the theory would give you. And now I can summarize. So the most important thing to remember is that there are some formulas that maybe you should check out. These are the Hall-Nernst and thermal Hall coefficient, which are valid beyond Boltzmann theory. The high temperature Hall anomaly in LASCO is explained by the TJ model, not quantitatively, but qualitatively at least. The Hall sign reversals in the flux flow regimes are also, these are actually quantitatively understood as effects of moving vortex charge that is defined through the Streda formula. So by that I will do, thank you.
So in this Hall sign reversal problem, when the vortex move, so the presence of impurity will not affect if there are impurity present in the superconductor. How will it modify this formalism?
So impurities in a flux flow regime they have two effects. If it's a short-range scattering effect of the impurity, it affects the Bardeen-Stevens conductivity of the core. That's essentially all gets lumped into the core conductivity. If it's long-range impurities and domain walls or things that are large compared to Xi, they can cause pinning. So there is a chapter in the papers describing what happens if part of the vortex lattice is pinned and part is moving. That changes the effective resistivity of the system because only part of it is superconducting and part of it is not. So your geometry is changing by the ratio of how much flux flow regime you have relative to the size of the system. Geometric effect. These are the two main effects, and they're quite simple to incorporate.
Okay, and one other question, is there any cutoff on the what will be the maximum charge of this accumulated charge near the vortex?
The charge depends on, logarithmically on the magnetic field, B over BC2, log of that. The coefficient depends on how sensitive the superfluid density is to the real electron charge. If the superfluid density is completely independent of electron charge, it's like particle-hole symmetry. That's what happens in the middle of a band, for instance. Everything is, the derivative with charge becomes zero. But I think incorporates is quite high relative to other systems because, again, we're near a Mott transition and things change fast as a function of doping there. But that's essentially the two quantities that go in. Then there's the electric constant in the third dimension. That's also important. So these are not universal quantities.
So I try to understand the physical reasoning why below the Mott transition you have this reversal of Hall sign. You cannot look at it as a reversal of Fermi's surface type, is it? It's not like, but you said it's effectively the holes are moving. Is that? But I couldn't get the basis.
Well, there are ways one can construct by fictitiously breaking symmetry, like thinking of a spin density wave and saying, oh, now we have small pockets instead of a large Fermi surface, getting it from there. But this is high temperature, even compared to those energy scales. So it's clearly coming from very local, strong interactions and not from Bloch waves of large coherence. So that it's a point I want to make because usually, right, one is based on some kind of a zero temperature picture that you then try to disorder. But here you're very far away from that zero temperature picture. What will happen at lower temperatures is, of course, not calculated here because it's high temperature expansion. And I would presume there's pairing going on and all the fun stuff that goes at low temperature. But the sign is already determined at high temperature.
So you presented formula for the derivatives of rho whole at b equal to 0.
Right.
If b is not equal to 0, it will not work. The quantity.
The formula is only applicable to that limit because I'm using the fact that in this intermediate formula I showed that I didn't explain too much, all the quantities were at zero magnetic field. And I needed that to throw away terms. For instance, the formula does not describe oscillations at, the Hassmann-Alfvén oscillations. Those come at stronger magnetic fields and require to modify the formula, which I haven't done. It's really strictly for this weak field limit.
But I mean, do you think there are equilibrium quantities that are there formulas of the type that you have presented at b not equal to 0 that relate some
I don't know, but it's a good question. I really don't know what. I think scattering will have to come in if you go to stronger fields, but based on, I guess, what we know from quantum Hall systems. Anyway.
I have a question. Like, suppose you have some different kind of superconductor, like which is modeled by, let's say, a Josephson junction array.
Modeled by what?
modeled by a Josephson junction array,
Okay.
where you have vortices that
Same Ginzburg-Landau theory.
same Ginzburg-Landau theory. So is there anything known about experimentally if the same effect is seen in those systems?
Well, one has to, the only parameters that are important for the whole theory is just how does the effective Josephson coupling change with electron density? And, okay, so that depends on materials and the junctions and so on, I don't know. But the Ginzburg-Landau is important. The log B part, because why does the log B come in? The log B comes in from currents which are far away from the core, so they're completely universal in terms of physics. They have a 1/r dependence on distance, and the magnitude is rho s, and they decay as 1/r. The energy density, the current squared, decays like 1/r squared, and that is proportional to the charge that is accumulated there, charge density. So integrate that on the unit cell, you get log of the size of the unit cell, which is depending on square root of b. So that's the log b. And it's not coming from core physics or pairing physics or stuff that creates
That was the idea, because I felt that that core part is out, so you just see this part here.
So, so the formula in your first part, what you mentioned, the formula of this to compute the resistivity or conductivity is generic. I mean, you can calculate sigma xx or sigma xy, as you showed.
The Kubo formulas.
I mean, the formula like this, you can apply. I mean, can be combined with numerics, for example, using this continued fraction or something.
This one?
Yeah, this part, yeah.
This is just a formal expression for the Kubo formula, DC limit.
Right.
I didn't show all the orders of limits that I showed before, but there are these orders that you have to take.
Yeah. So my understanding is that in your talk you applied this formula to the whole conductance or the rho h, right?
Yes.
And for the TJ model, for some other model, have you tried to use this? I mean, calculate the sigma xx itself, for the TJ model, for example. I mean,
no, because of the difficulties I mentioned before. To get sigma xx, you have to write the continued fraction expansion and extrapolate it to infinite order. Yeah. And that's always tricky. I mean, especially in 2 dimensions, the operators become very complicated, and you can't go to very high orders, so you maybe calculate 6, 7. I mean, better numerical people can do a much better job than I would imagine I can do. But still, there is the step that you have to extrapolate. You have to say, well, I got 7 recurrents, all the rest will just behave in the same way in some ways. So that is a barrier to actually give you a solid numerical result. But it's doable. I mean, I just didn't try it myself.
Yeah, so I couldn't really get the explanation for why in the TJ model at half filling, your RH diverges. Could you give a sense?
Yes. When you calculate the commutator of the magnetization with the current, you get extra factors of 1 minus n on the Gutzwiller projector.
I mean, mathematically, it's okay. I mean,
That is, well, okay, in the denominator, that will cause this divergence. Right. So it's really a property of the Gutzwiller projection, even at that low level, completely change the sign and the divergence behavior. You're asking physically why it happens?
Yes, yeah.
Well, the arguments that the experimenters gave from the beginning were somehow right, even though theoretically they're not talking about Fermi liquids, they were talking about semiconductor physics. So somehow the system knows it's coming towards an empty system of holes. Now, the problem is that the holes and the spins are strongly entangled, and it's not free fermions. And everybody who worked on slave bosons and all this stuff knows how difficult it is to handle these constraints. So those arguments really didn't hold water at the time, but they were correct. There is the fact that the only moving parts are the holes, and you have less and less of them, so the whole resistivity diverges. That's really the Mott physics, if you want.
Okay, thanks.
Okay, I think in the interest of time, we'll stop here, but you can continue the discussion.